In this video, we're going to continue to discuss one-dimensional motion, and we'll also derive the kinematic equations. Let's review some important information that we talked about last time. We said that if we have a graph of position versus time, and let's say it looks like this. If we have that graph and we want to know what the instantaneous velocity is at a particular time, I'll call it t1, we can determine that by simply looking at the graph at that time and finding the slope of the tangent. So the slope of the tangent to the graph at that time is the instantaneous velocity. We write that in this way. We say that the instantaneous velocity is the derivative of x with respect to t. And we're going to talk more about what a derivative is today, or how we calculate it. We also said that if we have a graph of velocity versus time, we can determine the acceleration from that graph. So let's say our velocity versus time graph looks like that. If I want to know what the acceleration is at a particular time, again, I just need to figure out what is the slope of that graph at that point. Now in this case, because I've drawn a straight line, the slope is constant. And so in this particular case, the acceleration would be constant. Again, we write this that the acceleration is the derivative of the velocity with respect to time. So how do we actually take a derivative? Well, this is something that you're going to be learning about in calculus if you haven't already. But I want to just show you quickly how to take the derivative of a simple power function. It turns out that taking the derivative of a power function is pretty straightforward. Here's the formula that we use. If we have any term like this, bt to the n, then the derivative of that term is given by this formula. And we simply take the derivative of each term at a time. Also, the derivative of a constant is 0. That makes sense. Remember that the derivative is just related to the slope. So if x is constant, then there's no change in x, and so the derivative is 0. All right, let's do the example of finding dx dt for this function. So the first term, 3t squared, so b is 3 and n is 2. What this formula says to do is bring the 2 down in front, so I have 2, I still have the 3 there, and then I have t, but I'm supposed to subtract 1 from the exponent. So I have 2 times 3 t to the 1. Okay? In other words, 6t. That would be the first term. Let's look at the derivative of the next term. Well, remember that 2t is really 2t to the 1. So I would bring the 1 down, in other words, not really going to make any change, and then I would have t to the 0. But of course, anything to the 0 is 1, and so I would just have 2 for that term. And then finally, the derivative of a constant is 0, and so my final answer for the derivative, dx dt, is 6t plus 2. Now remember, the derivative is the instantaneous velocity, so this would allow us to calculate the instantaneous velocity at any time t. Why don't you pause the video and try this example on your own. Okay, so let's go through it and see how you did. The first thing we want to do is find the equations for the velocity and the acceleration. The instantaneous velocity is just the derivative of x with respect to t. And so I'm just going to go ahead and take the derivative of each term. So again here, I'm going to bring the 2 down in front, multiplied by the 4. So that gets me 8. I'm going to subtract 1 from the exponent, so that gets me a t. For the next term, I've got a 1 here, so 1 times 4 is 4. and then I'm subtracting 1, so I have t to the 0, which is just 1. And then again, the derivative of a constant is 0. So that would be the correct answer for the instantaneous velocity as a function of time. Now let's take the derivative again. We know that the instantaneous acceleration is the derivative of velocity with respect to time. And so the derivative of 8t, I'm just bringing the 1 down, so I get 8, and then I get t to the 0, and so I just get 8. And of course the derivative of 4, since it's a constant, the derivative is 0. So the acceleration is just equal to 8. Notice this is a case of constant acceleration. Although the position changes with time and the velocity changes with time, the acceleration is constant. Now we're asked to figure out the values at a particular time. So where is the object, how fast is it moving, and what's the acceleration at t equals 2 seconds? I'm just going to plug into my three formulas. X is equal to 4 t squared, so I've got 2 squared, plus 4 times 2 minus 3. When you calculated that, hopefully you got 21 meters. To calculate the velocity at 2 seconds, I'm going to use the formula we just derived. So I've got 8 times 2 plus 4, and I got 20 meters per second. And then finally, for the acceleration is just constant, so it's just a constant 8 meters per second squared. So let's summarize what we've learned so far. Remember, we've defined displacement. We defined average velocity as the displacement over time. We then defined the instantaneous velocity as the derivative of position with respect to time. Remember, by the way, that this is simply a shorthand notation for our definition that says the instantaneous velocity is the limit as delta t goes to 0 of delta x over delta t. So this notation is simply a way to save ourselves having to write this thing every time. But remember, that's all it is. It's always a limit because it doesn't make sense to have a velocity at one time because time is down on the bottom. Okay, and again, most importantly for us, we know that that's related to the slope of the position versus time graph. We also defined average acceleration and instantaneous acceleration. Again, it's the derivative of velocity versus time, or the second derivative of position versus time. Key thing, remember, is if you've got a graph of velocity versus time, you can figure out what the acceleration is at any time just by looking at the slope. Also remember that position, displacement, velocity, and acceleration are all vectors, so the direction is important. In one dimension, we just deal with that with plus or minus. So if an object is moving to the right, it has a positive velocity. If it's moving to the left, it has a negative velocity. Let's look at the special case of motion with constant acceleration. The reason that we cover constant acceleration is we have one really big practical example, and that is anything that is just moving through the air where air resistance is not important. So for example, you take a ball, you throw it up in the air, it comes back down to you. That's an example of constant acceleration. Even if you take the ball and now throw it to someone else, again, it's a constant acceleration, which is just due to the force of gravity. So we've got lots of examples of constant acceleration. But we can also look at other ones. For example, if you're pushing on the accelerator in your car, or you're pushing on the brake pedal in a pretty even way, then we can certainly model that speeding up or slowing down as an example of constant acceleration as well. So what we're going to do is we're going to derive what are called the kinematic equations. And one of the nice things about the kinematic equations is once we derive them, we can solve problems without using calculus. So that's the good news. The bad news is that the kinematic equations can only be used for problems where the acceleration is constant. Okay, let's go ahead and derive a couple of these just so you can understand where they come from. We're also going to make an important notation change here. Okay, so what we're going to do is, instead of using 1 and 2 for initial and final, we're going to change our notation. No subscript at all means final. Okay, so instead of using a 2, if there's no subscript, that means a final value. The initial value we're going to represent with what we call naught. Okay, so naught, which is a 0, naught represents initial. Okay, so just remember, naught means initial. Say that a bunch of times to yourself. Naught means initial. Okay, so no subscript is final, means final. Naught means initial. The other thing we're going to do, just to make the formulas a little bit simpler, is we're going to set the initial time to be 0. Think about any motion you're looking at. Just imagine that you always make sure to start your stopwatch at 0. Okay, so we don't lose anything by doing that. All right, so let's see what we can do with this. Here is our definition of average acceleration. But because we're looking at the special case of constant acceleration, there's no difference between average and instantaneous. So instead of writing this formula with an a bar, I'm just going to write it with an a, because a and a bar are the same. The other thing I'm going to do is I'm going to rewrite this with our new notation. So instead of v2 minus v1, that would be v minus v naught, so final minus initial. And then t2, we're just going to write as t, that's the final time, and we're assuming the initial time is 0. Doing a little bit of algebra to rearrange that, I get that v is equal to v naught plus at. And that is our first kinematic equation. Now, I want to just look at what the significance of this formula is. What do you think I would get if I plot v versus t? Well, hopefully what you said is I would get a straight line with a slope equal to a and with a y-intercept equal to v naught. In other words, what you want to notice here is that this is just an example of what you've learned in math as y equals mx plus b. In other words, if you plot y versus x, you get a slope of m and a y-intercept of b. So notice the similarity in the two formulas. I'm plotting v versus t, so whatever in front of the t is the slope, just like when I plot y versus x, whatever is in front of the x is the slope. And then the other term correlates to b, the intercept. Okay? So notice that this makes sense. We're doing constant acceleration. So the slope of v versus t should be a straight line with a slope of a. Let's derive another of the kinematic equations. In order to do that, first of all, here I have our definition of average velocity that we've talked about before. And you'll notice here I've simply rewritten it with our new variables. This formula is another way we can write the average velocity. And it just says take the initial value, the final value, add them and divide by 2, and that should be the average. By the way, that's only true for constant acceleration, not generally true. And so what I'm now going to do is I'm going to take this and set them equal to each other. So x minus x naught over t is equal to v naught plus v over 2. And now I'm just going to do a little bit of algebra here. I'm going to bring the t over, and then after I've brought the t over, I'm going to bring the x naught over. So I'm going to do two steps at once. What I end up with is x is equal to x naught plus 1/2 v naught plus v times t. And that is a second of what are going to be 4 kinematic equations. I'm now going to take our result from before, that v is equal to v naught plus at, and I'm going to combine it with the equation that we just created to come up with a third equation. So what I'm going to do is I'm going to replace v with v naught plus at in this equation. So I get x is equal to x naught plus 1/2 v naught, but now for v here, I'm going to plug in v naught plus at. And then I still have a t out here. Doing a little bit more algebra, I get x is equal to x naught. Notice I have two v naughts inside the parentheses times 1/2, so I just get v naught t with that t on the outside. And then I have 1/2 at squared. And that is our third of the 4 kinematic equations. Now, if you look at that equation for x as a function of t, what is the shape of that graph? What kind of graph is that? Well, hopefully you answered parabola. And so if I plot x as a function of t, when I have motion with constant acceleration, what I find is that the position versus time is going to be some kind of a parabola. Now obviously it could be pointed up, it could be pointed down, it could be any part of the parabola depending on what the values of x naught, v naught, and a are. But it's going to be some kind of a parabola. Let's develop that idea a little bit further. I want to look at a couple different important examples. And so notice this equation gives us x as a function of time. This equation gives us v as a function of time. So let's look at what would some possible graphs be for first the case where the acceleration is not 0 and it's positive and it's constant. So in other words, the acceleration is just a straight line with a positive value. Okay, well, we know what v is equal to v naught plus at is going to be. It's going to be an increasing straight line. And with the case that v naught is 0, it's going to look just like that. If x naught is also 0, then when we plot x as a function of time, it's just the 1/2 at squared part, and that's going to be a parabola. So I want you to pay attention to this pattern because you're going to see it again and again with constant acceleration. Parabola, straight, and constant. Okay, so when we have a constant acceleration, the velocity graph is always going to be linear, and the position graph is always going to be a parabola. The only exception there is what if the acceleration is 0? So in other words, v naught, the initial velocity, is not equal to 0, and it's positive and it's constant. So v looks something like this. Well, the acceleration clearly is 0 because the velocity is not changing. So our acceleration is 0. And you'll notice that in this case, the position graph, since there's no acceleration, is now just a linear graph, x naught plus v naught t. And if x naught is 0, then we just get a linear graph like that. Okay, so if the acceleration is 0, the graphs simplify a little bit. We get a linear graph for x versus t, a constant graph for v versus t, and the acceleration is 0. Okay, so here are the kinematic equations. You'll notice that we derived this one and this one and this one. I did not derive the fourth one. You should be able to derive it from the other equations that are there. So deriving the fourth equation is just combining and rearranging a couple of the other ones, and you might want to try that on your own. One of the most important things to remember about these equations that we've just derived is they only can be used if you know the acceleration is constant. The other important thing to know is that all of the quantities are instantaneous quantities, right? No average values here, all instantaneous quantities. So in other words, v naught, the velocity when time is equal to 0. V, the final velocity when time is equal to t. X, the final position when time is equal to t. X naught, the initial position when t is equal to 0. So make sure that you understand these are all quantities that are instantaneous. They are the value at a particular point in time. Now you may ask yourself, why do we need 4 equations? Why did we stop at 4? Well, the reason is we have 4 basic variables, x, v, a, and t. And you'll notice that we now have an equation for we have 4 equations, each of which is missing one variable. So for example, in a problem, let's say that you know x and you know v and you want to know t. Well, first of all, if you only know x and v and you want to know t, we don't want to choose any equation that has an a in it because you don't know a either. But now look at this equation. We have x and v and t. So since we know x and v, we should be able to solve for t. And that's the way you pick what is the correct equation to use. So it's all about identifying what you know and what you don't know, and then picking the equation that only has one variable whose value you don't know. One question that I often get in my courses is, do I require you to memorize formulas for the exam? And the answer is, I don't. So I'm going to give you a formula sheet. However, that formula sheet is literally just going to have the formulas on it, like v is equal to v naught plus at. Sometimes what students don't realize is that there's a really important step before taking an exam where you're given a formula sheet. And that is, you must know what the symbols mean. And you also need to know what are the units for each of those. Okay? So what I would strongly recommend is start making a table. And the table should have 3 columns: quantity, symbol, and value. Because in a problem, I might tell you the initial velocity is 3 meters per second. Well, if you don't know that initial velocity is v naught, then the formula sheet doesn't help you. So start filling in the table. For initial position, earlier on in the course, we used 1 for initial and 2 for final. But now we're using naught for initial and nothing for final. Okay, so you want to make sure you're clear with those. Also, if the problem is in the vertical direction, we use y. So y naught would be the initial vertical position, and y would be the final vertical position. Initial velocity. Again, we used v1 very early in the course, but now v naught is our initial velocity, v is our final velocity. Time is now just t for us. Acceleration is a. Okay? And then again, make sure you know the correct units. Meters per second, seconds, and meters per second squared. And remember that really that's a shorthand for meters per second per second. You must use the correct symbols and units on exams. Okay, you must use the symbols that I've used.